In the last lecture, we discussed a little bit about how to handle curved boundaries and curved elements, and what we had said is we can handle them through appropriate mapping of the curved domain. Okay, so let me reinforce this point through a simple example. So let's say I have a domain which is like this. It has all these curved edges, okay, and I want to make a mesh of 4 quadrilateral elements on this domain. So what will I do? If I make the mesh as a figure, I will make of a mesh of straight edges. So let me do the following. I will take this and this. Okay. What are my nodes? Nodes will be this, 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 this. Now, if we have given a bilinear map here, then bilinear map, let's say this is my node 1, node 2, node 3, node 4, 5, 6, 7, 8, 9. Remember, let my approximation be of order P. So approximation is of order P. My mapping of the geometry from the physical to the master is through a bilinear map. In that case, if I take the bilinear map, then I will get the edges will be joined by these straight lines. So you see that the computer sees a domain, because why is this way? Because we have taken a bilinear map that is in each element I am giving the x is equal to sum of, in the element tau, let it be any generic element tau, I is equal to 1 to 4, okay, x I tau, and n I would say bilinear hat as a function of sin eta. Okay, similarly for y tau. So the x and y is given in terms of only these 4 corner coordinates of the 4 corner nodes of the element. Okay, so the domain that the computer sees is not the actual curved domain, but this domain, what we have obtained by the mesh. And you see that there is a tremendous discrepancy in the representation of the domain itself. Okay, the geometry is wrongly represented, and this will lead to errors in the finite element solution that you obtain, because you are solving for a different domain. So we would like to minimize the error in representing the geometry of the domain in order to control the error in the finite element solution. So the error in the finite element solution will have 2 parts. One is due to the geometry, so error due to the representation of the geometry, and you will have the error due to the approximation. Okay, remember that in most of the problems that we have done till now, in fact all the problems, for us the geometry that we had taken was polygonal. It consisted of straight edges. So the error in the representation of the geometry was 0. So we didn't bother about this. While this error was what we bothered about, and we discussed how to do mesh refinement and so on in order to control this error. Okay. Now, what will happen in this case? This error will be dominant, will be significant. Need not be dominant, but it will be significant. So how do you control this error? One way of doing controlling this error is to say, fine, let me refine the mesh. Can I take a finer mesh? Okay. Now see what we are doing. In taking a finer mesh, we are not going to take the points, these points of the finer mesh out of the previous mesh. We will have to move these points to this guy. So we will be taking the finer mesh in such a way that I have these as my edges. Okay. So you see that the error in the representation of the geometry also has gone down, as well as the approximation error, because as we had said that when the approximation is of order p, we refine the mesh, the error goes as h to the power of p. The energy norm of the error, or the square root of the strain energy of the error, goes as h to the power of p. But here also we have improved the representation of the geometry, and so the representation of the geometry is better and we can get better solutions. Now the question is, do we have to refine the mesh? Because when you refine the mesh, the cost of the computation goes up, number of unknowns goes up. So why not control the error in the representation of the geometry by doing a better representation of the geometry? That's what we had been talking about towards the end of the last lecture. So in doing that, what did we do? We said that we'll use a higher order representation, not the bilinear map, but something more. And we said, okay, let us take the serendipity quadratic map. Okay, so if we take the serendipity quadratic map for the same domain, okay, then how will I make the serendipity quadratic map for the same domain? So let me go to the next page. Okay, I will have my domain is like this. Okay, so we made this mesh to start off. Okay, 1 2 3 4 5 6 7 8 9. These are the nodes used to represent the vertices of the elements, not for approximation. Okay, so we said that, okay, let's now go to serendipity quadratic. Okay, in this case, if I take a generic element tau here, okay, what we are going to do, we will write our x in the element tau as sum of I. Serendipity quadratic has 8 nodes, x I tau ni serendipity quadratic hat as a function of sin eta. Okay, similarly y tau. Okay, in doing this, what do we have to do? So we'll have to put additional nodes in the element. So what we'll do, we'll put these nodes somewhere in the middle of the edges. You can put it anywhere, but if you put too close to any of these nodes, one of these existing nodes, then the mapping has a problem. So let's decide that we'll put it somewhere close to the middle of the edge. Okay, so middle of this edge, middle of this edge, similarly here. So we'll do it for all the elements. Will create these nodes which are in the middle of the respective edges. So I'll call these nodes by, remember that these are only for representation of the geometry. 12, 13, 14, 15, okay. So we have 21 such nodes. So if I am talking of this element, which this is my element 1, this is my element 2, 3, 4, then actually in element tau is element 2, the way I have shown. So we will have the x of 2, x of 11, x of 3, x of 13, x of 14, x of 5, x of 16, x of 6. Okay. So let's give a numbering pattern, and this gets mapped to the master square. How will it map? So this will be my, in the master square, 1, 2, 3, we'll call it 4. Numbering is something that is up to us. 6, 7, 8. So you see that the 2 here in the physical element becomes a 1 in the master, 11 here becomes a 2, 3 becomes a 3, 13 becomes a 4, 14 becomes a 5, 5 becomes a 6, 16 becomes a 7, and 6 becomes the 8. And these nodes are now in the middle of the edges. So this has coordinates -1, -1. This will have coordinate 0, -1. This will have coordinate 1, -1. So you see that this mapping takes us back to the same master square that we had earlier for the linear map or the bilinear map. Okay? So remember this, that we have this kind of a feature for the mapping. And so now, so we'll say mid side. If I do this kind of a fit where I am taking more points lying on the curve in order to represent the geometry of the element, okay, then we should do better than what we had done earlier, and you will see that you will get a very good fit as far as these edges are concerned. There can be errors, there will be errors. If this curve is not a perfect quadratic curve, it's something else, then there will be some errors, but that error will be small. So our representation of the geometry, that is the geometry that the computer sees, is much more accurate than the geometry that we had earlier with the bilinear map. Okay, that's why we should use a higher order map. Need not be always isoparametric. For example, if I'm using 8th order approximation, I need not use an 8th order map, but we have to use some sufficiently higher order map. Okay, it could be which is subparametric, could be, or it could be isoparametric. If my p is equal to 2 for the approximation, p equal to 2 here will do the job. Okay, so that is the idea, that is each geom has to be controlled. And you see here something curious, that in doing what we have done, we have ensured that the mapping is continuous. We have ensured that the mapping is continuous. Okay, what does it mean? That if I look at these edges, the common edges between two elements, there after the mapping I do not see a gap between the two elements. Okay, that is, it should not end up giving me a gap, that is a spurious space in between the two elements. And how is it ensured? You see on this common edge, the mapping is the same from both sides. It uses the same information, it gives me the same line on the common edge. So same curve on the common edge. Okay, this is one feature, that we have to maintain the mapping from both sides on this common edge. So naturally there will be no gaps. Okay, this mapping is invertible also, but finding the inverse, that is psi in terms of psi and eta in terms of x and y, is not so easy when it comes to higher order mapping, but one can do it. Okay, so these are some of the features of the mapping. Let me take an example to demonstrate this. How am I going to do it? Okay, let's say this is my domain with a centrally located circular hole. The mesh I am going to make is like this. This is the center, this, this. So this is the kind of a mesh you can make, mesh of quadrilaterals. Okay, let's say this inner one, the coordinate system is fixed like this, x and y. This point is located at R0. This point is located at big R0. Okay. So now, if I see that these are our initial nodes that we have created in the basic mesh. Okay, so let's look at the mapping of this element. Okay, so here if I take that element out, so let's first fix the corners, then we'll bother about the rest. Okay, so this angle is some angle theta, which can be obtained from this geometry. Okay, so this is point R0, this is point big R0, this is point R cos theta, R sin theta, okay. This one is point R, and here it will be the other coordinate we can easily obtain as, if it is a square, let's say it is a square, so this distance is R, we will keep this distance is also R. This is point RR. So let's say that this is point RR. Okay, the height has to be obtained, has to be given. So let's say this is distance R, this is also distance R, and this is distance R, and this is distance R. Okay, so we have these coordinates. Now we have to put these middle points. So the middle point here is nothing but R plus big R by 2, 0. Middle point here is R and R by 2. Middle point here is R plus R cos theta divided by 2, R plus R sin theta divided by 2. And the middle point here, what will the middle point here be? If this angle is theta, let me take this angle is, this will be theta by 2. This angle will be theta by 2. So this will be nothing but R cos theta by 2, R sin theta by 2. So this is how we can create the local coordinates. So I will call this one, local 2, local 3, local 4, local 5, local 6, 7 and 8. And using these coordinates we can go and construct the mapping. Okay. Then after we have constructed the mapping, then the rest is the same. That is, we need, from our computation point of view, we need to obtain del x del psi, okay, del x del eta for the matrix of the transformation, del y del psi and del y del eta, and in order to compute the Jacobian. Okay, so we compute these from the expressions for the x and the y in terms of the sin eta, that is in terms of the shape functions that have been used to represent the geometry. Okay, and once we have that, then we can obtain these expressions as functions of sin eta, and we are in business. So we can find the Jacobian, we can do everything else that we need. Okay, so this is how we are going to handle a curved geometry. Let me, while I am at it, let me harp on another issue. Let's say that I have this kind of a domain. Okay, let's say this is what, under some loading, let's say I have some loading acting on the structure, okay, some constraint somewhere, let's say I am fixing it, and I would like to solve this problem, find the state of stress everywhere in this domain under this loading and this constraint. So how do we do it? And let's say this is a planar problem. So in terms of the meshing, it's better to break the domain up into smaller pieces or subdomains, okay, and then do the meshing. So one thing we can do is break it like this. Okay, so we can right away break this domain into smaller pieces and do the meshing by pieces or meshing by subdomains. Why do you do that? Because this will give you a quite a nice looking uniform mesh, and it is not always possible to make the mesh by hand. So you use something called an automatic mesh generator, which takes the domain, the contours of the domain given by you, and gives you a mesh. So in these we have the feature of defining subdomains in most of the standard automatic mesh generators, and there we define the subdomains and then do the meshing by subdomains to get a uniform mesh, pretty good looking uniform mesh, such that the continuity is maintained, that is the nodes from the two sides should overlap. Okay, on the common edges the node should overlap. Okay, so like here on these edges, common edges, these nodes should overlap, and in doing this we can construct a fine mesh where we need the mesh to be fine. We can construct a coarse mesh in the region where we know not much is happening, so we can play around with the meshing and create a non-uniform grid or mesh which is in some way economical and also accurate in terms of getting you the solution. Now automatic mesh generator, writing it is very difficult. It is not an easy job. There are various procedures by which one can write an automatic mesh generator. There are methods like your paving and your advancing front method and so on, all those things. Now there are codes which are available on the net free of cost, which can be downloaded, which can do a very good job of automatic mesh generation in 2D. For two-dimensional domains it can be done. So you can go and download. There are some codes which is based on Delaunay triangulation, the concept of Delaunay triangulation, some which are based on the advancing front method, okay, and so on. So you can get these codes, download them, use it for your problem. Okay, so and the documentation also for these is available. Some of those codes I can take the names are, one is by Jonathan Shawchuk and the other is called Angener. So these codes are quite nice, they can be used. Okay, so let's now shift gears and go from this problem to a little bit of a different issue. That is, till now we have been talking about approximation or meshes where the nodes are overlapping. That is, we had ruled out such situations. This kind of a situation was ruled out. Why? Because you see that here, if I simply take bilinear, here you have a node here which does not have a counterpart from this side. So this is called a hanging node. So this was ruled out in what we did. We said that, well, this has to be taken care of, so either you do this and keep on doing it, okay, to fill up the thing, or you just can't do it. Okay, it turns out that it's not very difficult to have this kind of a situation and still ensure that your approximation is continuous. How do you do that? You do that by constraining this node. It is called, what does it mean? I'll tell you. That is, the approximation from this edge looks like this if it's a bilinear. Okay, the approximation from this side would look like this, okay, because of this node being present. So what you do, you force this approximation to exactly match this one. That is, you overlap this guy here, you overlap this guy here and force this one to get its value from here. Okay, so that is, on this side the approximation is given in terms of these nodal values, that is alpha 1 n1 plus alpha 2 n2. These are the n1 n2 are the shape functions from this side. Okay, so it will be like this. From this side the approximation is given in terms of, you will have alpha 1 bar n1 bar plus alpha 2 bar, I will call it n2 bar, plus alpha 3 bar n3 bar. I'm doing it loosely. This could be your n1 bar, this is your n2 bar, and this is your n3 bar. Okay, so you force, this is going to be u on the edge. Okay, force the u on this edge from the negative side to be equal to u on this edge from the positive side, which gives me a constraint on these degrees of freedom, alpha 1, alpha 2 bar, alpha 3 bar, in terms of alpha 1 and alpha 2. So this is called a constrained approximation. What is the advantage of it? Advantage of it is, let's say I have a crack here or a singular vertex here, okay? Then I can zoom in the approximation towards this without propagating this refined meshing elsewhere. So the cost of computation goes down, okay? So it's much more economical because I know here the solution is unsmooth, so I'll have to take care of it locally. So I keep on doing this kind of a local refinement, okay, to capture that unsmooth behavior, and I'm done, while the mesh elsewhere remains continuous. So you can see this in the literature. There is a very nice paper, I think published in 1989 by Odin, Westerman, and et al. Okay, in the computer methods in applied mechanics and engineering, this journal. So you can see this paper. It's very nicely, it describes how to do this job. Okay, let's now get down to again more classical things. Till now we have been discussing second order problems. Okay, where the highest derivative occurring in the differential equation was the second derivative, okay, partial derivatives. We talked of problems in terms of one variable, which was, an example was the steady state heat conduction problem, where temperature was the unknown, or the torsion problem, okay, where the warping function was the unknown. While we also talked of the planar elasticity problem, where we had a system of unknowns, that is two unknowns, which are the in-plane displacements u and v. Okay. Now let us look at a problem which is a fourth order problem. This is what we know as the, one example of it is the classical plate theory. Okay, it's attributed to Kirchhoff. This is called the Kirchhoff plate theory also. Sometimes the Kirchhoff-Love name is also added. Okay. Okay. This is a direct extension of the Euler-Bernoulli beam theory in one dimension. Okay. So how do we take care of, what do we do here? So here the idea is simple. Let us take a very simple problem, that is, I have a rectangular plate. Plate means it's the depth direction is much smaller, depth dimension is much smaller as compared to the in-plane dimensions. That is, here if this is my width b, this is my length. Okay, sorry, I'll put my coordinate system accordingly. So we'll put this as a, this is b. Okay, then this one, this dimension here is t. So we'll say that t by b, t by a is much smaller than 1. So let's now, as you saw that there is a difficulty in writing things, let's fix a coordinate system. Coordinate system is such that I have, this is my x direction, this is my y direction, and this is my z direction. Okay. We assume the thickness is uniform. So T is uniform everywhere. That is, it does not change with the x and y location, and it's a rectangular plate. Now, if you see, this coordinate system is such that this height is t by 2. So it's in the middle of the thickness of the plate. So on top you have t by 2, bottom you have t by 2. Okay. What we'll assume further is that this plate is loaded by only a distributed transverse load. Under the action of this transverse load and suitable boundary conditions, what are we going to do as far as the boundary condition is concerned? We are going to constrain the transverse movement of the plate on the edges. That is, we are going to force the transverse displacement on this edge to be 0. Okay, it's an extension of the pin support in one dimension. So here we will have that W, the transverse displacement W is equal to 0 on the boundary. That's it. So this is what we have as our, and there are no other loads applied on the structure. The transverse load we have, W is 0 on the boundary. This is what we are going to take. Okay. Now for this problem, let us see how are we going to get the solution. So there is a standard way, what we call as a St. Venant semi-inverse method, where, or in the strength of material way, you try to figure out what is going to be the deformation pattern. So here for this plate, it can be shown when it is thin that sigma xz, sigma yz, sigma zz are essentially 0. That is, they can be ignored or neglected with respect to sigma xx, sigma yy and sigma xy. That is, the magnitude is much smaller as compared to those. Okay. We further have an assumption here that the transverse straining is much smaller as compared to the in-plane straining. That is, EZZ is on top of this assumed to be 0. So this gives us the plane stress assumption. Okay, and this is the additional assumption that we make for the classical plate model. Okay, let us assume that we have an isotropic material with Young's modulus E and Poisson ratio nu. Okay, so if I go ahead and expand what we have made as our assumptions out, sigma xz in this case equal to 0 implies the engineering strain gamma xz is also equal to 0. Sigma yz is equal to 0. This implies the engineering strain gamma yz is equal to 0. EZZ is equal to 0. This will imply that del, the transverse deflection, del W del Z is equal to 0, which is what we are going to make, that W is only a function of x and y. Okay, so this is the first outcome of this assumption. This will imply that del U del Z plus del W del X del Y, sorry, my mistake here, del, I was working with the wrong thing, del V del Z plus del W del Y is equal to 0. Okay, this will imply del U del Z plus del W del X is equal to 0. So this assumption will lead to V as a function of x, y, z is x, y minus z del W del Y, and U as a function of x, y, z is U0 xy minus z del W del X. Okay, where did these things come from? These assumptions say that a plane perpendicular to the middle plane remains perpendicular to it after deformation, just like we had done in the beam, that a line perpendicular to the middle line remains perpendicular to it after deformation, okay, and that line does not stretch in length. So these assumptions give us the representation of the displacement field. It can be further shown that in this case, for the isotropic plate, okay, the values of V0, the functions V0, U0 and V0 will be 0 everywhere, because they will be governed by the planar elasticity problem. Okay, it turns out, because of this being a bending dominated problem, that the only displacements that you are going to have is W, and due to the W, the U's and the V's will come. So in this case, for this kind of loading, we will have only the W being non-zero, U0 and V0 will be 0. If I had an in-plane loading along with this transverse loading, then yes, we would have U0, V0 also. If I had anisotropic material, then also U0, V0 will be present. So remember, in this very special case, U0 and V0 become 0 functions. Okay, so now we can write what is the strain. Okay, Exx will be del u del x, which is equal to minus z. I'm going to write everything now in short form, w comma xx, which is del 2 w del x squared. Eyy will be equal to del v del y, which is going to be equal to minus z w comma yy, and gamma xy, these are the only strains which are non-zero in this model. Okay, this is equal to del u del y plus del v del x, this is equal to minus 2z w comma xy, because you see from here you will get minus z w comma xy, from here you will get minus z w comma yx. Okay, so both yx and xy are the same. So this is the state of strain. Now what about the state of stress? State of stress will be sigma xx, because it is plane stress problem, because of the assumed state of stress, you will get E by 1 minus nu squared into Exx plus nu Eyy. Okay, so this I can write as E by 1 minus nu squared into Exx will be minus z w comma xx minus nu z w comma yy. Similarly, I will have sigma yy is equal to E by 1 minus nu squared Eyy plus nu Exx, which is equal to E by 1 minus nu squared into minus z w comma yy minus nu z w comma xx, and sigma xy, which is sometimes written as tau xy, is equal to g into gamma xy. This is equal to E by 2 into 1 plus nu into minus 2z w comma xy. So we have the state of strain and the state of stress for this problem known to us. Now we are going to use the total potential energy. We are going to write the total potential energy expression in terms of the state of stress and the displacement given to us. Okay, W is not known, but we will write it in terms of W. And then how are we going to obtain the equations for W? By saying that W, the solution W, is the minimizer of the total potential energy. So here we are using the approach of the variational formulation. We could have used the principle of virtual work, or we could have used the differential equations, okay, to get to the weak form. Okay, so next is we will write the strain energy U is equal to half integral. Let's go back to our figure that we had earlier. We will call this whole plate is said to have a volume V, okay, and this face, if you look at the projection of it, this area will be said to have an area A, okay, and for the area we will have the contour, the bounding edges, which will be given by delta A, such that these bounding edges are arranged in a counterclockwise manner. So this is the naming convention we are going to follow. So the whole volume of the plate is V, the projected area of it is A, this is the same through the depth, okay, and the bounding contour of the area is called delta A. So in this case, U becomes integral over the volume of sigma xx Exx plus sigma yy Eyy plus sigma xy gamma xy dV. Okay, this, if you write, will be equal to half, we can write it as this, integral over the area. You see that the volume becomes essentially integral over the area into integral for z going from minus t by 2 to plus t by 2 of sigma xx Exx plus sigma yy Eyy plus sigma xy gamma xy into dz dA. Okay, so we can say we will put this within the brackets. Now, because why are we doing this? Because we know the expansion of the UVW in terms of Z explicitly. So we would like to eliminate that dimension, which in terms of our mechanics means that we are looking at equilibrium or the responses or the forces not in terms of stresses, but as in terms of its stress resultants, which are the moments, the shear forces, and so on. Okay, so this integral here we will get as this is equal to half integral over the area integral over z, okay, of, now we will have E by 1 minus nu squared into sigma xx Exx. So from the previous one we will have Exx squared plus nu Exx Eyy plus from here Eyy squared plus nu Exx Eyy plus g gamma xy squared. Okay, because this is what sorry, not g here, we will have, I made a mistake, it will not be g here. If you go back to what we had done, this will become 1 minus nu divided by 2 into this, because E into 1 minus nu by whole squared, I have taken it out as common. Okay, so this will be E by 2 into 1 minus nu squared integral over the area integral over z. Now let's expand this thing, it will be z squared w comma xx whole squared plus nu, in fact 2 nu z squared w comma xx w comma yy plus z squared w comma yy whole squared plus 1 minus nu by 2 into 2 sorry, not 2, we will have, if I go back to the expression for my gamma xy, it is actually equal to 2z w comma xy. So we will have into by 2 into 4 z squared w comma xy whole squared dz dA. Okay. So you see that here through all these things we have this z squared sitting in each one of these expressions. Okay. The integral of z squared and the rest of them are all functions of only x and y. The w comma xx, w comma yy, w comma xy are all functions of x and y. So they are functions in terms of the area only. So we can explicitly integrate out the part corresponding to the z. So z squared integral from minus t by 2 to plus t by 2 will be z cube by 3 evaluated from minus t by 2 to plus t by 2, which will be equal to t cubed by what will you have, t cube by 12. Okay. So t cube by 12, so u will be equal to actually e into t cube by 2 into 12 into 1 minus nu squared integral over the area w comma xx whole squared plus w comma yy whole squared plus 2 nu w comma xx w comma yy plus 1 minus nu 2 into 1 minus nu because of this last expression. 4 divided by 2 is 2. Okay. 2 into 1 minus nu into w comma xy whole squared dA. So you see now we have integrated out the effect of the part of corresponding to z to get this expression over the area. Okay. In terms of the function w, which is a function of x and y only. Okay. If you look at this expression here, this is given a name d, which is called bending rigidity. Okay. So essentially it tells us how rigid is the plate in bending, how much it resists bending action. Okay. So we have this expression for u. Similarly, V is equal to the minus of the work done by the external forces. So here the work done by the external forces is integral over the top area, which is nothing but the projected area itself, because we have said that the in the depth direction the cross section or the profile does not change. So this will be equal to q xy into w xy. W is constant with z. Okay, so it doesn't change from the top to the bottom, this much. So then our pi as a function of w, this is a functional, will be u plus v. Okay, and the solution to the problem, so the goal is find w which minimizes pi. I, as we had done earlier, the first variation of pi is equal to 0, which is then equal to the first variation of u plus the first variation of v. And this, if you work out, will be quite easy. How do you work out the variation? So essentially it's like taking the differential or derivatives of these quantities. So we'll end up getting delta 1 pi is equal to integral over the area d into w comma xx del w comma xx plus w comma yy del w comma yy plus 2 nu w comma xx del w comma yy plus 2 nu w comma yy del w comma xx plus into 1 minus nu w comma xy del w comma xy dA minus integral over the area q del w dA. This is equal to 0. This is our virtual formulation. Okay, so this is the virtual formulation that we are going to get out of what we have obtained here. Okay, sorry, I think the 2 will go away. Yes, I have made a mistake here. Actually, it will be 2 divided by 2, so this 2 will go away. It will not be present there. This 2 will not be present there. So I will only have the news here. Okay. So this one should also work out to see, but I had made a mistake there. So once we have this formulation, then now we are in business. We can solve the problem. In order to solve the problem, we have not yet done any approximation here. We have simply posed what is the definition of the displacement or representation of the displacement. From there we went to the state of strain, to the state of stress, obtained the total potential energy, that is, we wrote the functional. From there we did a minimization of the functional to get the virtual formulation. And this is the approach one has to follow in all the problems where we can easily obtain the energy expression. Okay? So you need not always go from the weak formulation, you can go from the virtual formulation also, whichever is convenient, we use that. Now you see the problem that we have, an interesting thing is here w comma xx, w comma yy, w comma xy is sitting. So what we have here in this problem, that we want w comma xx, w comma yy, and so for del also, comma xy should be defined. If they are not defined, then the energy becomes meaningless because it becomes infinite. Okay, and the right hand side in the virtual formulation, I would say this is the left hand side, will also become infinite. Okay, so this should be defined, which implies that we want that w comma x, w comma y, and so with del w, okay, should be continuous. Okay, that is, we need C1 approximation minimum for the representation of this W. Okay, so minimum smoothness required is C1, that is the first derivative of W with respect to x and y should be continuous. Okay. Now if you let me reiterate that the places where W is defined, what do we know about del W? At those places del W has to be constrained to be 0. Remember that in the places where W is defined, del W has to be constrained to be 0. Now in this problem, just like in the Euler-Bernoulli beam, in the Euler-Bernoulli beam we also had the rotations, that is del W, del X. They could also be defined on the boundary. Similarly here we could have on the boundary the slopes or the rotations del w del x, del w del y defined. In that case the delta del of delta w del x and or delta of del of delta w del y should be 0 correspondingly. That is, in terms of the slopes also we will have geometric constraints, just like we did in the Euler-Bernoulli case. However, for the problem we have taken, it is simply supported, that is w is 0 on delta A, and on this edge when we go and do things properly, this means that we also have the normal component of the moment is 0 and the tangential component of the moment is 0 on the edge. So if this is the edge, here this component of the moment is 0 as well as this component of the moment is 0. So this is m normal, this is m tangential. So you see on the edge a bending moment and the twisting moment, both are 0 in this case. This is one of the so-called simple supports. This is in fact a so-called soft simple support. Okay, you have a hard simple support also and so on. What if this edge was free? If an edge was free in that on that edge, your mn mt, that is the resultant moment, bending and the twisting, as well as the normal shear force V will also be 0. Okay, so that would be a free edge. But the bottom line is, in all these cases, the work done by the forces on the edge is 0. Okay, that's why it didn't come in our definition of the total potential energy. We could have moments and shear forces applied on the edge, then we will have to account for it in the expression for the total potential energy. Okay, so in the next time onward, in the next class, what we are going to look at is how to construct the approximation. Okay, that is, what are these basis functions globally? Okay, which means what are the element shape functions. Okay, here we will see that we can construct one family of basis functions globally which will not be conforming, in the sense that they will not ensure continuity of del w del x, del w del y everywhere along the edges. Okay, that is, if I take the plate and mesh it with rectangles, then along these edges del w del x, del w del y will not be continuous, they will only be continuous at the node points. Okay, so this is actually violating our requirement, but it is shown that this does a fairly good job. We could, however, at least in this case, construct the strictly conforming approximation, that is, use the extension of the Hermite cubic polynomials from the 1D to the 2D, but for the rectangular mesh, and then we will have the conforming approximation. So we will look at both the cases, the not strictly conforming and the conforming, in the next class.